Chapter 3, Think and Explain. Problem number 51. Is a fine for speeding based on one's average speed or instantaneous speed? Explain. Well, it actually could be either. I remember at times in the past when I have been driving through rural areas, rural areas also use the radar guns, but occasionally I've seen signs that say speed checked by aircraft. And in that case, that is an average speed that's being measured. That it has two landmarks that can be seen from a helicopter or a plane, and it can time how long it takes you to get from one of those landmarks to the other. So if it knows the distance and divides by time, that is finding average speed. And if that's in excess of how fast you're going, then you get a speeding ticket. They'll then contact somebody or they'll take a picture of your license plate. More often than not, though, instantaneous speed is the one that is being used, and that's the one used by radar gun. Basically, the way a radar gun works is it sends out radiation, electromagnetic radiation. It hits an object, and the radiation reflects back, and then the detector detects the radiation that comes back. There's a shift in the frequency of the radiation when it hits the vehicle that's moving and comes back, and based upon how much the frequency shifted indicates how fast the object was going, and so that's more of an instantaneous speed. Now, if you want to make an argument that it's still an average, but over a very tiny amount of time, you probably could make that argument. That's when you start getting into the nuances of calculus. Calculus is actually look at slopes based upon infinitesimally small changes in time, the essence of a derivative. But for practical purposes, it is an instantaneous speed. Problem 63. For a free-falling object dropped from rest, what is the acceleration at the end of the 5th second of fall, 10th second of fall? Defend your answers. All right, I am prepared to defend my answers. So there are some assumptions that are being built into the problem that are not stated, but most people would not think about the exceptions. But we are assuming that this does take place over a short period of time, a short distance of fall. That we're not talking about something that is falling, 1,000,000 miles over 5 seconds. So that would be something with an incredibly large gravitational pull for a relatively small object. In other words, very high acceleration due to gravity. Now, if we're talking about Earth, over 5 seconds, an object's going to fall maybe 50 meters be traveling about 125 meters, and that is small compared to the size of the Earth. And so that's over a short period of time, so we assume that the acceleration is close enough to constant. Now, if you're falling 125 meters, there is actually a very small difference in the acceleration due to gravity, but you need the multi-million-dollar equipment in order to detect that. Anything that we would have here or at most universities, you would not be able to notice the difference. So one of the assumptions, though, when you're dealing with free fall, and when we say free fall, we're saying the only force acting on it is the force due to gravity, is that the acceleration is constant. That the acceleration is the force divided by the mass. The force is the weight. Weight is mg. So mg divided by the mass, which is m. The masses cancel out, and you're left with g. The acceleration is the acceleration due to gravity, and so it is constant. 64. If air resistance can be ignored, how does the acceleration of a ball that's been tossed straight upwards compare with the acceleration if simply dropped? And this goes back to Newton's second law, which we'll go into more detail in chapter 4. But the acceleration is the force divided by mass. The force on the object is the object's weight. Now, as long as the mass is not changing for this object, the force stays constant. And so if the force is constant and the mass is constant, the acceleration has to be constant. It is downwards the entire time. Now, as the ball is going up, the acceleration is in the opposite direction, so it slows down. As the object's falling, the acceleration is still down and it speeds up. If you recall back to class, acceleration and velocity are both positive, or both the same sign, then it speeds up, so that they're both positive or both negative. If the acceleration and velocity are opposite signs, it slows down. So again, the sign, a negative acceleration does not necessarily mean it's slowing down. Positive acceleration does not necessarily mean it's speeding up, but it comes down to what is it in relation to the velocity in terms of sign. But in this particular case, ball tossed straight upwards, the acceleration, as long as there's no other forces acting on it, the acceleration stays constant. Now, what about the hand? I've had some students think about the hand involved, but we're talking about once the ball has already left the hand, or whatever's projecting it upwards. has been tossed straight upwards compared with the acceleration if simply dropped. Again, the acceleration is constant over a relatively short distance of time, and I say relative distance of space, and relative is based upon the size of the planet usually, or the moon, or whatever the astronomical body is that's attracting the object. 65 is a very similar problem, that when a ball player throws a ball straight up, by how much does the speed of the ball decrease each second while ascending? In the absence of air resistance, by how much does the speed increase each second while descending? Again, the change in velocity is the acceleration, is change in velocity over change in time is the acceleration. So if we assume same time intervals, because it says for each second in both cases, so same time interval, the acceleration is going to be directly related to the change in velocity. And, well, and while the ball's in the air, again, we're ignoring air resistance. The only force acting on it is the force due to gravity. And so the acceleration is the acceleration due to gravity. On Earth, about 9.8 meters per second squared. Depends upon where you are. It fluctuates, as we talked about in class, presumably. And so as it goes up, speed will decrease by 9.8 meters per second every second. As it falls, it'll increase by 9.8 meters per second every second. Those are the same accelerations because both of those accelerations are pointed downwards. Same vector acceleration because they're both pointed downwards.